So in this video we will be discussing about law of radioactive decay. Now what we can generalize from this is, say suppose this particular sample has a number of nucleus. Now this nucleus is radioactive and so it will undergo decay. It may be alpha decay, beta decay or gamma decay. It can be any of this. Now one thing that we are sure of is that the amount of decay that is going on with respect to time is directly proportional to the number of nuclei that is present in that particular sample. So this is my sample. So that we can understand this logically. So how much amount of decay will be there? What is the quantity? That quantity will depend upon the total number of samples. So the more the number of samples, the more decay it will be. So now we know that del n upon del t is proportional to n. So in a way we can say del n upon del t is equal to lambda into n. Now this is equal. So we are using a proportionality constant, and this proportionality constant is called as radioactive decay constant. Let me use a different color. This is known as either radioactive decay constant or it is also known as disintegrating constant. Disintegrating constant. Therefore, if you want to see the change in number of nuclei in that sample, say suppose this is dn. So dn is actually equal to minus n in time del t. So this can be written as dn, change in dn in time dt is equal to minus lambda, that is the proportionality constant, because it is always decreasing, so minus lambda into n. So this is one thing that we can arrive by thinking this in a logical point of view. Now if I take n over here, let me do the calculation at this part. Please have a look. Now dn upon n is equal to minus lambda upon dt. So this is a slight modification that we did. Now if I integrate both sides, upon n equals to minus lambda upon dt. Now my integrating constant will be now from a amount n naught, that was from initial amount n naught to the final amount say n, and the time will be from our initial time t naught to the final time t. So the result, I am writing the result over here. What is dn upon n is nothing but a ln. So here you have ln n upon n naught. I'm just using integration. This integration becomes ln. This becomes n minus ln n naught. So this can be written as ln n by n naught, which is equal to now this term becomes minus lambda was already there, t minus t naught. So this can be written as ln n by n naught minus lambda t minus t naught. So far we have proved this. Now say suppose we are taking this from our initial condition. T equals 0 is from our initial condition where the decaying has now started, or we have taken the time at t equals to 0. So you have ln n upon n naught is equal to minus lambda t. So this is what you had achieved. Now if you look closely, this is a logarithmic function. And we can change this into if you look closely, we can change this into n of t is actually equal to n naught e to the power minus lambda t. So this is our final conclusion. So if I write this in a proper way, n upon t is equal to n naught e to the power minus lambda t. Now I have often seen the students get confused regarding this. So let me simplify this. If we are talking about log a to base e is equal to c, if this is our conclusion, log a to base e base c, then if we break this in power notation, we can see that e to the power c is equal to a. Now if a is in turn n upon n naught, then n becomes, if this is a is equal to this, then n becomes n naught e to the power c. Now what was c? C in our case was minus lambda into t. So e to the power c becomes minus lambda into t. So this is the logarithmic notation that we have used. This is as simple. If log a to base b is equal to c, then we can write base e to the power c is equal to a. This is a way of writing in a log form. E to the power c equals to a can be written as log a to base e, which is equal to c. So in this way, we can have an idea about, or we can understand a bit about the law of decay. Now, by further calculation, we know the rate of decay. If you define R as the rate of decay, so R is actually dn upon dt. This is what R is actually, which has a minus sign. So now, if I prove this further, R equals to minus dn upon dt. And what was n? N upon t was nothing but here, as we have proved earlier, n upon t was nothing but n naught e to the power minus lambda t. So if I differentiate d of n of t upon dt, then I'll have minus lambda into n naught into e to the power minus lambda t. So therefore R for me dn upon dt, that is n, if I differentiate n, then for me R becomes, this is minus and this is minus, so minus minus becomes plus, which is equal to lambda into n naught into e to the power minus lambda t. Now if you are thinking about this minus, R equals to minus dn and dt, and dn and dt is minus lambda, so minus minus gets cancelled. So this is R. And what is actually this particular quantity? If you look at this particular quantity, lambda into n naught, this was the initial condition. So we have R equals to rate of decay is R naught lambda n naught e to the power minus lambda t. So sorry, I just wrote one step extra. So R naught is actually equal to lambda into n naught. So this equation can be converted into R naught e to the power minus lambda del t, that is to the power. Now this is also a one form of radioactive law. This is also radioactive law. This is also one of its form of radioactive law.